Fellow learners, this is Cameroon GCE, Ordinary Level Chemistry 0515. And we will be starting today with June 2024, Paper 2, Section B. As I told you, you are new to this channel, please take some time and subscribe to the channel so that all the other videos will get to you. Remember, this channel, we don't ask money for it. I don't ask money for this channel. My main goal is for you to understand the basic concepts of chemistry and be future engineers, future pharmacy students, future medical doctors, future educators in aerospace, engineering, agriculture, and different fields of life. That is my goal for you people. Thank you for taking your time to subscribe. Let's get started. We are on Section B. In this section, you are required to answer all the 2 questions in this section. So here it has to do with qualitative analysis. Qualitative analysis. Now, with question 6, it reads: a student was provided with 3 salts, X, Y, and Z, alongside with some laboratory equipment and the following reagents. We had aqueous sodium hydroxide, aqueous barium chloride, and dilute hydrochloric acid. A series of tests were carried out as shown on the following table. Study the table, study and complete the table. Okay. We have the test procedure, we have the observation, and we have the conclusions. Learners, I know by now your teachers must have carried out some few qualitative analysis experiment on cations and anions. That's the positively charged metals and the negatively charged non-metals. So you are supposed to have carried them out with, according to the syllabus, with aqueous sodium chloride, aqueous ammonia, aqueous sodium hydroxide, aqueous silver nitrate, and a flame test. When you have all these, you should be able to answer this question. Let's move on. They say to 2 cm cube or 2 cubic centimeters of solid X is added 5 drops of sodium hydroxide and warmed. A solution, remember we were given salts and you have to prepare these solutions. A solution is a combination when a solid, that is a salt, dissolved in a solvent. When you dissolve a solid in a solvent, for example, distilled water, you have a solution. So that solution have been prepared. Solution of X, solution of Y, and solution of Z have been prepared in that way. Adding a known amount of water to that solution and adding a known amount of that salt into a known amount of distilled water to prepare that solution. Now we are saying in A, to 2 cm cube of solution X that was prepared, we added 5 drops of aqueous sodium hydroxide and warmed. Now, the observation is this: a colorless, pungent gas is evolved that turns damn red litmus paper blue. What is now the gas that is being produced? When you are doing experiment in the lab, observation is very, very important. What is being evolved? That is, Do you see do you see a gas being produced? And the indication of a gas being produced is effervescence. You could see bubbles coming out from the solution. You could see heat that is being produced. Everything you see out is being outlined there. It's from there that you can bring out your conclusion. So for instance, okay, reaction of this salt with aqueous sodium hydroxide, what will produce? Look at what's happening here. Let me just go back again for revision purpose. That is what I want you, when you are at home, try to do this so that you'll be acquainted with what is done in the laboratory. Look for a table like this one. Okay, for instance, look at what I want to show you here. You must have a qualitative analysis table like this. That has to do with sodium hydroxide and has to do with ammonium. But now we are saying that what is being added? It was added and a gas is being produced of that salt. A gas is being produced. So what do you think should be the salt? What do you think is being produced? And it turns damn litmus paper, damn red litmus paper blue. Then you also have to know the test for all the gases. From one of those salt, okay, you from the observation, you can draw inferences. You can draw conclusion from the nature of the gas. Now that you know the nature of the gas, you can now go for test for gases. Test for gases, you can come here. That's what I want you to do when you get back home. Go for test for gases. Okay, turns damn red litmus paper blue. Which gas is that? The only gas that turns damn litmus paper blue is ammonia. It's only ammonia that turns damn litmus paper blue for test for gases. This is what you are supposed to know. Now, for ammonia, okay, look at the color when it reacts to be sure that it is ammonia. What is being produced when that substance reacts with what? Will react with aqueous ammonia. We were told when it reacts with aqueous ammonia, what is being produced? Look at it again. Take your time. A colorless pungent gas is evolved. And that gas is what? It turned damn red litmus paper blue. So now we have not been given about anything concerning precipitate. Don't bother yourself maybe thinking about what precipitate, since no precipitate was given based on the observation. Work your answer based on the information you have been given on your question paper. Now that you have been given information only on guesses, go but only to where your guesses, where you can recall in during the examination room the different tests for guesses. And if you go to the different tests of gases, one, damn red litmus paper blue, and a pungent gas. These are the all description for ammonia. And see how it turns, how it does. For ammonia, you see what happens with ammonia? This is it. Ammonia, it turns it blue. And this is how you can observe it in the laboratory. This is how you can observe this in the laboratory. It turns a damn red litmus paper blue. This is it, and it is a base. Remember, ammonia is alkaline. Is alkaline. That is basic. Ammonia gas is basic, so it will definitely turn damn red litmus paper blue, and it has an irritating or a pungent type of smell. So after doing that, after knowing that this is ammonia that is being produced, you now go to your question paper, your answer sheet, and conclude there that the gas produced is what? Is ammonia. Your conclusion is ammonia gas produced. That's what you have to write. Once more, write your answer based on what is given on the question paper. Ammonia gas is being produced. Ammonia gas Can put it NH3 is produced. Ammonia gas is produced. Now, so our conclusion was based on our observation. We go to 2. 2 says a sample of X, the same solution, is strongly heated in a test tube. That same solution was heated in a test tube. And when it is heated in a test tube, what happens? It says our observation is that a brown gas is evolved. When this sample, a sample of X, we are not saying that a solution of X. Remember that this is a solution. These are salts. This one is a solution, but a sample of X was heated. And when you are heating this, there's no water there again. The other one was a solution, but this one is a salt. On heating this, remember that on heating this, a gas is being produced. There's a reaction with oxygen. That is a gas is being produced. And if you know your test for gases, a brown gas that is being evolved will definitely be nitrogen dioxide. That is the gas that is being produced. But it should be remembered that in the first case, the aqueous ammonium, in the first case, remember that it was a solution. There was a solution, and this one is just the salt. Now let's go to B. B to 2 cm cube of solution of Y. Therefore, Y has been dissolved in water to form a solution. That is now is an aqueous solution of Y. We don't know why. Aqueous solution of Y. So now to just tell you what happened with this one here. In this occasion here, I want to show you what happened here. When ammonium gas, let me say, when NH4, when NH4, which is solid, is being heated. I think there is an equilibrium. There is an equilibrium that is being established. It sublimes. We say it sublimes. It sublimes to produce. What we call ammonia gas plus hydrogen chloride gas. Hydrogen chloride gas. These are all gases that are being produced. Okay, now let's move on. This is for the purpose. That's why I say note. This for the purpose of revision. Note for revision purposes. Okay, now let's go to B. To 2 cm cube of a solution of Y. We don't know why. Now, is added 2 drops of aqueous sodium hydroxide. Okay, now, what is our observation? Observation is not given. But what is the conclusion? They have told us that iron 2 ions are present. Iron 2 ions are present. When a certain salt, a solution of that salt is added, reacts with aqueous sodium hydroxide. Go to your table, as I told you, reaction with sodium, aqueous sodium hydroxide and the reaction with aqueous sodium hydroxide, you will see that there is a certain salt that is being, there is a certain salt that reacts with sodium aqueous sodium hydroxide that releases what? Ion 2 ions. And what is that salt? And what will be the observation? Okay, if we go to our table of with cations reaction with sodium hydroxide, you will see that on adding aqueous sodium hydroxide, there is it here. On adding aqueous sodium hydroxide to a certain solution, aqueous sodium hydroxide to a certain solution of salt that we don't know, it will produce what? Ion 2 ions. And what will be our observation? The observation is what? It has green precipitate will be formed. Therefore, you can conclude that the salt that react with sodium hydroxide producing green precipitate produces what? Ion 2 ions. So that salt should be an ion salt. It should be an salt that contains an ion. Therefore, what will be our observation? Green precipitate remains on adding excess sodium hydroxide solution. That is what we have here. Green precipitate turning brown in contacting with air and insoluble in excess. Green precipitate are formed. Good. So what do we do? Well, let's go there and write green precipitates are formed. Green precipitate are formed. So our observation here on B will be what? Our observation on B here will be green precipitate are formed and remain on adding or are insoluble on adding excess sodium hydroxide. So here is green precipitate. Green precipitates formed insoluble in excess. You can say insoluble briefly. Insoluble in excess sodium hydroxide solution. Yeah. So our observation here is green precipitate formed and do not dissolve, or we say insoluble in excess or on adding excess sodium hydroxide. They will give you a point there. We go to 2. The 2 cubic centimeters of a solution of Y is added 2 drops of barium chloride. Now the whole game has changed now. Barium chloride is now being added to the salt that contains what? Barium chloride is now being added to a salt that contains an ion. Okay. It's added 2 drops of barium chloride solution, followed by dilute hydrochloric acid. Now you now see there's a reaction that's going to take place here. Okay, there's no observation, we don't know, but an ion is being produced. Fellow learners, again, also remind you, go back to your table of qualitative analysis for anions and see the one for carbonate, the one for nitrate, the one for nitrates, the one for sulfates, the one for sulfides. This is a sulfide ion that is being produced. So you should know what is the observation in the production of sulfide ion. For revision purpose, let me take you there. On your sulfide ion, for anions, these are anions. This is the one for anions. For anions, you will see that for the sulfide, you will see these are the sulfide ion that are being produced. These are the sulfide ion that are being produced. Sodium, you say it is sulfur dioxide being released with dilute acid. We added what? Aqueous or dilute hydrochloric acid. So in that case, there was a sulfide ion that was being produced. And what would definitely be the gas? The gas will be a sulfur dioxide that will be produced, because sulfur dioxide is being produced or is being liberated when a dilute acid is being added. So our observation will be what? Our observation will be, okay, our observation here will be what precipitates are formed with barium ions. So what precipitate are formed with barium ions. Sulfur dioxide is also being is also being formed or produced. That is just all. Sulfur dioxide is being produced. A gas which is sulfur dioxide is being liberated. 2, it will also give white precipitate with barium ion. That is just all. Let's go back there. Sulfur dioxide is being formed, and the word gives white precipitate with barium ion. Go back to your question paper. Go back there. The first thing you do here is what? SO2 gas is being produced. The first thing is SO2 gas is evolved. Because this gas is evolved on adding dilute acid. Then 2, this is the first one. Then the second one is what? Gives white precipitate with barium ion. Forms white precipitate with barium 2+. So that is that's it's just that you don't need 2 points. You don't need to go. Sulfur dioxide gas is evolved, and again it forms white precipitate with barium ion. That's all. Okay, now if you do that, we will now go to the C part of it. That's our observation. Now, the C part of it, 1, it says C1, we don't know, but the observation has been given. Z gives a brick red flame color. Okay. As I told you, when it has to do with qualitative analysis, know your reaction once more. Know your reaction with aqueous ammonia, with cation. Know your reaction with aqueous ammonia, with aqueous sodium hydroxide with cation. Know your reaction with all these solutions again with anions. Know your flame test. Know your test for your gases. Now on the flame test, which metal gives a brick red color on a flame? Which metal gives a brick red flame on heating? That is you have to know. So now what you need to do here is the metal that gives a brick red here, 1. How are we going to describe this? So what we will do is the metal that we are going to describe here is the procedure, because here we need to know the procedure. This is the procedure that we need to describe. Describe the procedure and give us the results. Let me give you the procedure. The procedure now is how to carry out a flame test. That's how you have to describe how a flame test is being carried out. Let me briefly describe it here for you. how a flame test is being carried out. Let me describe here how a flame test is being carried out. We can say it is C1 here. C1, C1. This is how you can carry out a flame test. Now, what do? You can say to salt Z. You can say to the salt, to salt Z. What you will do is to salt Z in a watch glass. That is a watch glass. A watch glass is a bowl like this. It's a bowl like this. That's how a watch glass is. Then you put the salt in here. You cannot put the salt in here. Okay. To salt it in a watch glass. In a watch glass, add a few, we can say, yeah, add a few, let me say add a few, add a few drops of concentrated hydrochloric acid. Because with acid, that's what usually happens. Add a few drops of concentrated HCl, hydrochloric acid. Add a few drops of concentrated hydrochloric acid. Then 2. That's the first point. This is the first point. The second point, how you can do that in that procedure, place a small amount of Z on a nichrome wire. Place a small amount of the Z on a nichrome. On a nichrome wire. That is, then the last stage should be what? The last stage of this is, now the nichrome wire containing the small Z is placed in the hot blue part of the Bunsen burner. Place the nichrome wire containing salt Z. Salt Z is placed in that hot blue part. Okay. Now, what am I saying here? Let's say this is a nichrome wire. This is a nichrome wire. Then you take pieces, you place dilute hydrochloric acid, place a small amount of Z on a nichrome wire. Then after adding concentrated sulfuric acid into this salt, Then you take the nichrome wire. On the edge of the nichrome wire, you place a small amount of the mixture of the salt. Then you take this nichrome wire, go to where the flame is. This is where the flame is. Let me say this is the flame. Where on the blue part of the flame, that is where you place the salt, and you will see the color of that will be generated from there. So precisely, I am saying to a salt zit in a wash glass, add a few drops of concentrated hydrochloric acid. 2. Place a small amount of zit on a nichrome wire. Then the last section is the nichrome wire containing salt zit is placed in that hot blue part of a Bunsen burner, Bunsen flame. That is how you do the experiment, and you observe the color that will be generated on the blue flame. Okay, if you write that, then if you summarize this here on C1, you have your scores. Then they said a brick red flame is being produced. Okay, now that was the observation. Now again, what is the conclusion? What gives a brick red flame with the salt? The salt that gives a brick red color is usually a salt containing calcium. Salt that gives a brick red color is salt that contains a calcium. So you can conclude here. Your conclusion should be that salt zit contains calcium ion. Salt, you can say salt contains, apologize for my poor writing. Salt zit contain, you can say salt zit contains calcium ion. It contains calcium that is Ca. Your conclusion is salt zit contains calcium ion. That's what you are. That's what you are supposed to put. Or you can just say calcium ion present. Okay, you can put it there. Another way of putting it like that. You can say calcium ion present. You can say okay, calcium ion present. That's another way. That's the way you can just put it. Or you can say salt zit contain calcium ion or calcium ion present. Finish. Okay, let's go to your experiment will have about 2 points. Then your conclusion had just 1 point. Just the description I gave you, 2 points. Your conclusion 1 point. Now, C2. What is C2 saying? C2 says to 2 cubic centimeters of a solution of zit is added 5 drops of dilute hydrochloric acid. I described it without, I've already described it over there when we're doing the tests. So, to 2 cm cube of a solution of zit is added 5 drops of dilute hydrochloric acid without heating. Good. A gas is evolved, which turns lime water milky. That's good. So now, what salt will definitely evolve a certain gas that will turn lime water milky? Once more, learners, I told you, go to your test. When you see like this, get back to your test for gases. Which gas can turn, what should be ringing in your mind is, which gas turns lime water milky? Oh, it should be carbon dioxide. And what salt usually give carbon dioxide? Oh, carbonates. Carbonates will always release carbon dioxide. So for the purpose of revision, I just want to tell you that carbonates will release carbon dioxide. Nitrates will a salt of nitrates will release nitrogen dioxide and nitrogen monoxide. Salts of sulfates and sulfites will release sulfur dioxide. So when you see all these gases, you should know the type of salt that will release them. That is just a tip I'm giving you. So now, the gas that will turn lime water milky is what? It's carbon dioxide. So now, be thinking of the salt. The salt should be from where? It should be from a calcium carbonate, because we have already got some calcium up here. So, okay, our conclusion is what? Okay, an acidic carbon dioxide gas is evolved. Good. Acidic CO2 gas is evolved. Good. So by doing like that, a gas is evolved. And what is a gas? Acidic carbon dioxide gas is evolved. And that is a gas that will turn lime water milky. Okay. Now, after having all this information, learners, now the examiner wants to test if we can now know what are our salts. Okay. From the table, identify X, Y, and Z. Okay. From Z here, we saw calcium, and we also saw a gas, carbon dioxide, that was released. Therefore, I said only carbonates will release carbon dioxide. And one of the carbonates is calcium carbonate, because there's a calcium ion that was identified here. So let's start with Z. Our answer for Z, the salt for Z is what? Is calcium carbonate. Good, let's write it. Z is calcium carbonate. Calcium carbonate is being released. Calcium carbonate, which is a limestone. You can put it limestone in bracket. Limestone. Calcium carbonate, that is a salt. And you write it as that is a salt. Now let's go to Y. What is a salt? Y is which? Y is which of the salt? Well, if you look at it, I said an ion is there. If you look at Y from all what we had, okay, from Y here we saw that, okay, there was an ion that was being produced. Okay, if that ion was being produced, then again we saw that below the B there was a gas that was being produced, a sulfur dioxide gas that was being produced. If ion is there and that a sulfate is there, okay, the salt should be what? And the ion there is what? It's not ion 3, but it's ion 2. So what should come? It should be an ion salt, ion sulfate, ion sulfide. That's what is bringing in our mind. And the possible answer for this is ion 2 sulfate. Good. So our possible answer for Y is ion 2 sulfate. Ion 2 sulfate, or what we call the ferrous sulfate. Another name for it is ferrous sulfate. Ferrous sulfate. And what is the formula? The formula for this is FeSO4. That is the formula. Now let's go again. What is the identity for X? The identity for X, always go to your conclusion and you get it from there. Your conclusion, you get it from there. Now, Our conclusion was what? Ammonia gas is produced. And then there was a nitrogen gas that is there, which is a brown gas. So what should be the salt? And I told you on heating, go back again, I gave you a hint here that when silver or when ammonium chloride is heated, ammonia gas is being produced and hydrogen gas is being produced. So this ammonium chloride could be the salt. It could be the salt because when this reacts, you will see what it produces the ammonia. So therefore, what should be our conclusion? Our conclusion is ammonium chloride salt. Good. Ammonium chloride salt is our conclusion for X. Ammonium chloride. Ammonium chloride salt. And this is how it is written. N that is it. Ammonium chloride salt. So our identity is the ammonium chloride salt, ferrous sulfate, and calcium carbonate. These are our three salts that we were given in our practical lesson. Let's go to E. What is E? E says to prepare and collect a dry sample of ammonia gas in the laboratory, the following equipment and the chemicals are provided: a round bottom flask, delivery tube, a clamp, and a stand, drying towel, a gas jar, solid ammonium chloride, solid calcium hydroxide, and a quick lime. Draw and label the experiment setup that you will use. Okay, fellow learners, I just want you to do this. When you have this, if your teacher must have shown you in the laboratory, you should be able to draw this. I will just show you the sample of it and you should be able to draw it when you have time in drawing this. So this is this is your experiment I have designed here for you, and you will know how you can draw it when you have time. That is the experiment. Here you have the round bottom flask. Here you have the ammonium chloride plus the calcium hydroxide here. You have the stand that is here. This is the delivery tube. You see it here. It delivers the gas right to this level. You see the Bunsen burner, the tripod where the round bottom flask sits on. Now, you have the quick lime that is here. The quick lime is used as a dryer in that experiment. The quick lime is used as a dryer in this experiment. Then you have the iron stand that helps to get the the jar that's holding the jar, and the gas that is being produced is ammonia. After calcium oxide, the quick lime has dried the gas. So that's a good setup. In your exams, you can have this. You can prepare for this for your revision. So that is the setup for question number 6E. That is the setup for question number 6E. Laboratory preparation of ammonia gas. Preparation of ammonia in the laboratory. Thank you. Let's go to F. F is, let's get back to F. If we get back to F, F has to do with the F section. So the F section, The F section, complete the table on the separation of a mixture. Okay, and the table says, okay, the separation technique, the mixture, and the physical property of components that enable separation. What we are looking for now is what technique is used, and what are the properties that will enable us to do the separation. Now, fellow learners, your teacher must have taught you how to do different types of separation. Separating the type of separating soluble salts dissolved in water, how you can separate it from another, how you can separate the salt when mixed with maybe sand, the different separating solution that can dissolve like spirit in water or like oil in water, how you can separate them, the different method of separation techniques. But we are specifically to this one that has been given here. And we are dealing with what? The mixture here is what? Different color pigments in chlorophyll or in a colored ink. In that case, we are using but a paper chromatography. A paper chromatography is the method, the separation technique that is used in separating colors. Chlorophyll, let's say you grind chlorophyll, take a leaf and grind it, and you want to separate it. That is a color mixture. So the color in ink, the ink we use in the classroom every day, it has many colors. Let's say we want to use the ink now. How can we do this? The separation technique for this is what we call the separation technique is chromatography, paper chromatography. We can say paper chromatography. Let me put it here. Paper chromatography. Paper chromatography. Okay. So I can say paper chromatography. Paper chromatography. That is the separation technique used in separating colors, different colors in a sample that has been given. Now, the physical property of the component that enables their separation is what? Is the physical property is what we call the retention factor. The retention factor, or what we call the RF value. Every component has its own RF, the retention factor. Every component in the ink has a retention factor. So the RF value. You put the RF value. The RF values. RF value, that's the retention factors of the different components in the color. For revision purpose, you may not understand this provided your teacher has not given you. This is it. Let me show you. The method of separation of colors. Take for instance, we have two glass jars. Now I will put the solvent there. There are two things: the solvent and the solid that dissolve. So the solvent is always the water. The solvent is always the water. Let's say this is the solvent. This is the solvent here. That's the water. We have two jars. This is a jar here. This is the solvent. Then we take a paper. On that paper, we drop a piece of ink. Or we grind a piece of leaf that is green or that's yellow. We can take the solution and drop there. So we want to separate the components of the colors. So when we drop it here and allow it to be in water, this solution here will dissolve. Remember, the solvent is moving up. The paper absorbs the water. The water is moving right up. It has a distance that is going to travel. We call it a mobile phase. So as the water is traveling up the paper, what happens? The ink that is here will dissolve and will also be carried up, or also travel up the same distance. But remember, the ink here has different colors as indicated here. These are the different colors in the ink that are traveling up. We have black, we have red, we have blue, we have orange, we have red, and we have yellow. All of them, when it's dissolved in the solvent, they will travel at different level. And all these colors, the different colors that make up this ink, will travel here at different distances. And these distances are the ones that are going to help us to distinguish them. That this one is purple, this one is red, this one is orange, this one is yellow. And how do we do that? We take the starting point where the ink was as the original point. Now from there, we are going to calculate the distance traveled by the water. We call it the solvent. And the distance traveled by the different color components. And that's how we are going to calculate our RF value, which we call it the retention value. Let's go below. Let me show you further again. Here, this is the ink. It has to travel up. We call this ink, you see, this solvent, and this is the ink, and this is the paper. Okay, this is how the ink travels up. So you see the level of the solvent, that is the water level, has traveled here. Or the one with orange, this is its own level that has traveled. That is direction of the solvent flow. Okay, you see green, this is their own level that has traveled. This is red. Okay, what we will now do is this. The distance travel, the RF value now, see how we are going to have the RF value now will be what? The distance traveled by the solid divided by the solvent. Okay, let's get back again. Distance traveled by maybe the solid is, let me say it is yellow, it is blue, it is orange, or it is red, divided by the distance traveled by the solvent, which is water. This is well explained here. That's how we do it. So now let's say A travel a distance from here to this level. That is the solid, A. But the solvent, which is water, has traveled a distance right to this level here. So our RF value will be distance traveled by A, which is A, divided by distance traveled by the solvent, which is B. When we have this value, there is a table. At this level, you may not have it, fellow learners. There is a table, all the table of all the different liquids, all the different components, they have their RF value there. We will take this value, go to that table, and refer the corresponding value, and will now identify that, okay, this component A is this component B is this component C is this. That is how the RF value is being calculated. Okay? That is how we do separation techniques in liquid, in components, when it has to do with separation of components with color. Thank you very much. Let's go now to question number 7. Question number 7 has to do with, it is quantitative analysis. I want to believe so. Question number 7. Question number 7 has to do with qualitative and qualitative or volume measurement, quantitative analysis. Yes. In order to determine the concentration of a dilute acid, a student is provided with the following solutions and equipment. 0.2 molar sodium hydroxide is reacting with hydrochloric acid, dilute hydrochloric acid. Of course, an acid and a base reacting, or an acid and an alkali reacting, is a neutralization reaction. Pipette, burette, a conical flask, phenolphthalein indicator, a clamp, and a stand. Draw the setup for the experiment. If you have been watching my previous video, you should be able to draw this diagram. So now, let's get there. Okay, let me draw the diagram here for you. I have a sample here that you just have to go through it. You don't need to, when you have time, you can draw it for yourself. In this experiment that I've just described, the question I've just described for us here, this is how it is. We have a burette. This is how a burette is being drawn. This a burette. And now we have a clam, we have a stand, we have a conical flask. This is the analyte. Then we have a burette. Inside the burette, we have already put in, we have pipetted a certain amount of, let me say, the base into this, into the conical flask. Now there is the acid that is being added here. The acid is here. This is the acid here. Now we start our experiment. We have a phenolphthalein indicator. When we do this, we drop a phenolphthalein indicator there. Then what happens is that we start titrating. We start titrating. That's we start running the acid from the burette into the conical flask. This was the initial level, and this will be the final level. And the final level is the final reading point. And that's when there is a change in color. We call it the end point, where it changes to this light purple color after the addition of phenolphthalein indicator. So this is the setup. If you were asked to draw this, you can put this on your paper. Thank you very much. Let's go to B part of it. The B part of it says, excuse me, the B part of it. What is B part saying? B part is saying 25 cubic centimeter of 0.2 molar sodium hydroxide was transferred into the conical flask, and the 3 drops of a indicator were added. Name the apparatus used in transferring 0.2 sodium hydroxide into this conical flask. The apparatus that we use in it, we call it a 25 because they have said 25. 25, go back to my laboratory section in my previous paper, you will see what I am telling you. You will see what I am telling you, please. So we will use a pipette to transfer this there, to transfer 25 25 ml into this conical flask. So we call it a pipette. 25 we call it 25. Name the apparatus. B1 is 25 ml pipette. So 25 ml pipette. 25 ml pipette. Yeah. That will transfer the the sodium hydroxide into it using the 25 ml 25 ml pipette. State the color change in the conical flask. Of course, from here you have seen the color that is there. You have seen the color that is there. In this our experiment, you have seen the color. State the color change. This is the first, when we transfer the sodium here, we now add the phenolphthalein indicator, it will be blue. It will be somehow, yeah. But now at the end point, this is the end point. That is the end point. So it will be from what? From pink to very faint pink color. Okay, let's go back to our question paper there. Our question paper says, state the color change. The color change in the conical flask is what? The color change is from pink to very faint pink color. Okay, from pink to very this color, this pen, okay, use it this way. faint pink color. Okay, from pink to very faint pink color. Now, let's go to the C part of it. Now, in titrating it, look at it very well. If you look at from our titration here, look at our titration very well. Look at our titration very well. Okay, we have, this is the initial point. Of course, the initial value should be higher than the final value. This is the initial value. Let me say, I don't know, maybe it's 50 ml. Let's just see from here. Then maybe after titrating, it gets to maybe 20 something ml. So 20 something, 50 minus 20 something, we will not have our final value. That has the amount of the acid that has been used up. Okay, let's get back to the onboard, to the question section where the data has been given to us. Now, this is the data. The data that has been given. Our bureau reading, the approximate reading, the first accurate reading, and the second accurate reading. In this thing, the appropriate, we are not going to, the approximate, we are not going to use the approximate values. We are going to use the accurate. These approximate value are values, we call them a testing value, or we call them rough titration. We call them the rough titration to know, it's just making us to be conversant with the volume we are going to use. If we have something like that, then we should be figuring out what will be our right or our accurate value. So this is carried out as a rough titration. So now let's complete the table. Okay, what we are going to use is going to be let's complete the value. Our tetra is what? Our tetra is supposed to be okay, now determine. We will put it up here. Determine the mean tetra. The mean tetra here is complete the table above. Let's complete the table first. Okay, the approximate here is what? Is the approximate value here is supposed to be, the approximate value here is supposed to be 26 point. That is the final minus the initial. So the final minus the initial will give us what? It will give us 26. So 26.2 minus 0.2 will give us 26.00. It should be in two decimal places. Yeah, that's what we are supposed to have for our approximate value. Then let's go to our accurate and second accurate. So now in this value here, we started it with what? We started it with our initial value was this. It came right down to this level. So it is supposed to be 25.10. 25.10 cubic centimeters. Now, on the other side, our second accurate should be 24.9 because this divided by this, I mean this take away this is 24. 49.0 minus 24.1 will give us again 24.90 cubic centimeter. Okay, we have the approximate, which is the rough titration. We have our first accurate titration and our second accurate titration. Then we have completed one. Now determine the mean value. The mean value is between the last two accurate titration whose value are almost the same. Okay, and what will be the our mean titra? Our mean titra Our mean tetra, determine the mean tetra from up here. The mean tetra from up here should be our mean tetra. Our mean tetra here is how do we calculate the mean tetra? We will have 25. Our mean tetra, we are going to take this and we are going to take this. That's what we are going to use in calculating our mean tetra. So our mean tetra will be 25, 25.10, 25.10 plus 24. 25.10, sorry. 24.90 all over 2. All over 2. So all this so what do we have? Our value would definitely be 25.00 cubic centimeters. That would be our main HCl that was used. That is 25.00 cubic centimeters of hydrochloric acid was the value that was used in the titration. That is our mean tetra. Let's go now to the D part of it. The D part of it, calculate the concentration of the acid if 25 cm cube of 0.025 molar sodium hydroxide was required. From our mean tetra, we already have 25 cubic centimeters of hydrochloric acid. And now they are telling us we should use, if 25 cm cube of 0.2 molar sodium hydroxide was required, then everything is equal. The ratio is 1:1. So now, what do we do now? Okay, since the first thing in the good thing you have been written, you have been given a balanced equation, so you don't have anything to bother yourself. We can now use, there is a formula, we say it is the molarity of the acid, volume of the acid, divided by molarity of the base, and the volume of the base. In our equation, we have the acid, the ratio of the acid to ratio of the base, which is the alkali sodium hydroxide, which is there. And if we do that, what we are looking for is what? We are where A is the molar ratio of the acid, and B is the molar ratio of the base or the alkali, that is the sodium hydroxide that was used. Now, we are looking for what? Calculate the concentration of the acid. We are looking for MA. We are looking for MA. And if we want to look for MA, after this manipulation here, MA times VA times B, and all will divide all by V. We will divide MB, VB, A by what? By VA and B. So by making MA the subject, MA should be what? MA, which is the molarity of the acid, should be what? MA should be MB, as I said, MB, molarity of the base, and volume of the base, times acid, the molar ratio of the acid, divided by let me see, excuse me, my rough writing. Divided by the volume of the acid, and the molar ratio of the base, which is B. Yeah. And if we substitute our value here, MB is 0. MB is 0.02 molar, that is 0.2 molar, 20 molar, times B, the volume of the base is what? Okay, the volume of the base, we have to convert it into liters. And by converting it into liters, we have to divide it. 1 liter is equivalent to 1,000 cubic centimeters. So we have to divide it by 1,000. So if we convert the volume 25 into liters, we will have 0.025 liters. 0.025 liter times, the molar ratio of the acid. In this equation, 1 mole of the acid is reacting with 1 mole of the alkali or the base. So the ratio is 1:1. So times 1 divided by, the volume of the acid. The volume of the acid was what? It was 25. This is what we calculated from our titration. It was 25. But we have to bring it down. We have to convert it into liters. So what do? We divide it by 1,000 cubic centimeters. And it will give us 0.025. 0.025 liters. Now we have to multiply it by what? By the molar volume of the base. The molar volume of the base was what? The molar volume in the the molar ratio, the molar ratio of the base in the equation. The base here, or the alkali here, is sodium hydroxide. Only 1 mole of sodium hydroxide reacted with 1 mole of hydrochloric acid. So I said the ratio is 1:1. So times 1. Now, how do we cancel out our points now? Let me see if there is a way out here to cancel our points. Okay, we can cancel the points out in this way. Okay, our liters will cancel this. Our liter will cancel this one. We are now left with only the molar. So now, if we multiply 0.20 molar times 0.025, this 0.025 again will also cancel this other one again too. So we are left with 0.20 molar. So our answer now will be what? Our answer here will be 0. It will give us what? It will give us 0.20 molar. So we can now say concentration of hydrochloric acid. Concentration of HCl will be equal to what? 0.20 molar. And that is our answer. That is our answer for this section. Okay, let's go to section. If you do it like that, then you are done with your quantitative analysis, volume measurement. Let's go to the diagram above, the diagram below. Section E. The E part of this is telling us the diagram below show different method for the collection of gases in the laboratory. Study the diagram and complete the following table. Okay, now diagram A, diagram B, and diagram C. Okay. Diagram A, the gas goes down. Diagram B, the O up. Diagram C, okay. bubbles will be produced in C. In that case, there is water there and the gas will go above the water. Okay, let's come to a conclusion. Now, for diagram 1, which is A, method of collection. What is the method of collection of A? Downward delivery. Is downward delivery because the gas comes here right down. A downward delivery. Downward delivery. In other words, you could say upward displacement of air. Because when the gas is collected down, the air is being displaced and the air goes up. Okay, so the method here is, the method for A is downward delivery. Let me change my color. Thank you. Okay, we say it is downward delivery. Here we have A is the method is downward delivery. Downward delivery. That's for A. It's a downward delivery. You could also attach it there as upward displacement of air. You can still say upward displacement of air. That's another way. Upward, you can say in bracket, upward displacement. So, downward delivery is an upward displacement of air. And the method, example of gases that are collected by this method are, we can say, you can now hear the example of such gases are gases like chlorine gas. We can say chlorine gas. Okay. Chlorine gas, chlorine or hydrogen gas. Chlorine or hydrogen gases. These are the gases. You can say chlorine gas or hydrogen gas or hydrogen hydrogen chloride. Sorry, it's a hydrogen chloride. HCl. Hydrogen chloride gas. I say it's chlorine or hydrogen chloride gas. So these are the gases that you can collect, chlorine or hydrogen chloride gases that you can collect through this method. Then method number, the second method here is for B. For B, you see it, I say it is an upward delivery, just the way you see it, upward delivery. B is upward delivery. Upward delivery. B is upward delivery. Another way for upward delivery, you can now say that word is, another way for upward delivery is downward displacement of air. You can still say downward displacement of air is acceptable. So when the gas is going up, air is being displaced downward. So we can now say downward displacement of air. You can say downward displacement of air. Upward delivery or downward displacement of air. That is another way of putting it. No need writing it. Now, what are some of the gases? What are some of the gases that are collected by upward delivery? Some of the gases that are collected by upward delivery are what? We have gases like ammonia. So most of the gases like ammonia, the gases are soluble in water and less dense than air. So gases like ammonia, gases like ammonia gas. Okay. Okay, ammonia gas. Ammonia gas is an example of the gases that are collected through this method. So now, ammonia gas, example of gases that are collected through this method. Then let's go to number 3, number C. You see number C here. Number C is there is water here, and they want pass it through water. You see bubbles, and the gas goes up. So how is that method called? We call this the collection method. We call it collection method. We call it displacement of water. Collected over water. We can say displacement of water. By displacement of water, displacement. So this method here is displacement of water. The method here, we call it displacement of water. Either you call it displacement of water or collected over water. You can another way you can put it as collected over water. Collected over water or displacement of water. That's the method that you use in doing this. And the example of such example of gases collected in this way are what? Example of gases collected through this method by displacement of water or over water are gases like we say they are gases like carbon dioxide. We say they are gases like hydrogen. We say they are gases like oxygen. These are these gases. These are the gases that are collected in that. Carbon dioxide, hydrogen, and oxygen are good example. Once more, on this section, I said, looking at A, the delivery method of this gas is a downward delivery, or you can call it an upward displacement of air. Then the type of gas here is chlorine and hydrogen chloride gases. Go to B, this method B here. Now B is an upward delivery, or we can still call it downward displacement of air for B. And the gas for B is ammonia gas. Then we go to 3. We say it's ammonia gas because the gases are soluble in water and less dense than air. Then C, we are saying that since it is collected over water here, because there will be bubbles of water here, the bubbles of gas that you will see here in the water, we now say the method of collection is collected over water, or you can say by displacement of water. Then the gas produced here are what? Gases collected through this method, we say they are carbon dioxide, there is hydrogen gas, and there is oxygen gas. These gases are insoluble. These are insoluble in water or are slightly soluble in water. That is why they are collected above the water. Because in your exam, they could ask you, why do you think the one is a downward delivery? Why do you want the one is an upward delivery? And why do you think the one is collected above water? That is why I am mentioning these things there. Thank you. Fellow learners, we are done with section B. We will be starting again with section C. We will be starting again with section C. For now, those of you who are not, who have not subscribed to my channel, please take some time and subscribe to this channel. take some time and subscribe to this channel so that other subsequent video will get to you as soon as they are done with. Thank you very much. Once more, my wish is that you do your best in your exam and become and aspire for better careers in life. Thank you very much. Bye-bye.